This is video number 54 on the foundations of arithmetic, algebra, and graphing with a focus on real-life interpretation and application. My name is Bill Kinney. It's part 13 of a subseries that includes an emphasis on spreadsheet usage. In the last video we looked at an example where we were looking at a bank account that for your principal, your initial deposit was $1,000 and your interest rate was 0.1%, which is pretty accurate these days. Your money grows very slowly. The graph that we got was almost straight. It's this graph right here that's blue, but is ever so slightly concave up, and that's what happens with compound interest is you get a graph that is concave up, though if your interest rate is higher you'll get a graph that's even more concave up. And in fact, let me go ahead and change the interest rate now to something unrealistic, something high like 10%. 0.1. Notice I'm making the change up in cell B2. It's going to affect everything else. It'll affect the balance over time. It'll also affect the average value. Let's see what happens. There we go. The balance grows a lot faster now. After 10 years it'll grow to almost $2,600. The average value is of course higher too. And I don't know how well you can tell by looking at this picture here, but the red graph, now the horizontal one for the average value, is not now halfway between the extremes of 1,000 and almost 2,600. It's a little lower. The 1684 value here is smaller than this number, which is halfway between the extremes, halfway between 1,000 and this 2593.7425. And that's what happens with concave up graphs. If I make it even more extreme, like a 25% interest rate, we'll see this process even more clearly, hopefully. Let me make it even more extreme. There we go. There's a 50% interest rate. Money growing at 50% or a population growing at 50%, the average value is definitely a lot lower than halfway between the extremes. 15,000 type 45 is a lot lower than 29,332, which is halfway between these two things. Before I go on to thinking about something else here, I want to show you that averages can be found using another built-in function called sum, equals sum. Before I used equals average to find these numbers here. This was for the whole column C5 colon C15 were these numbers here. This one was equals average C5 comma C15, indicating just those two numbers. The colon indicates all of the numbers, the comma indicates just the two. You can also find averages by adding up the numbers. So I did equal sum and then dividing by how many numbers there are. So I can just do a divide by 11 here. There are 11 numbers. That'll average those 11 numbers, and it'll be the same thing, 15,545.011. Alright, so there are plenty of built-in functions in Excel. Alright, next thing I want to show you is, let me change this back to something more realistic. Well, I'll go to 2%. Next thing I want to show you is a depreciation example. This is actually a depreciation example that I looked at, I don't know, it was maybe about 7 or 8 or 9 videos ago. And we're buying a car for $25,000, and we find that it goes down in value, depreciates to $21,500 after 1 year, estimate its value after 3 years, estimate it when its value will be $6,000. And in the previous video, we created what I call the linear depreciation model that gave us the value, which I'll call V, as a function of time, t, f of t, v equals f of t, and the slope of this was negative 3,500. That gets multiplied by t, and then the vertical intercept, the v-intercept, is the initial amount, 25,000. That's a linear depreciation model, and we use that to answer the questions. But that's not the only model that we could use. We could also use an exponential depreciation model, but this is not exponential growth, it's exponential decay. v equals f of t equals, it turns out the initial amount, 25,000, times some number, which I'll just leave blank for the moment, to the t power. What number should go inside the parentheses? Well, it's going to be what's sometimes called the discount factor. It's going to be a number that indicates the percent that the value after 1 year is compared to the initial value. In other words, it's, in this case, 21,500 divided by 25,000. That number, which is going to be a decimal between 0 and 1, is 0.86, meaning after 1 year the car is 86% of the original value. That is the number that's going to go in here, 0.86. That'll be my exponential depreciation model. Let's compare these models. They will give us different answers to these questions. Which one is correct? Which one is the right answer? I don't know, to tell you the truth. I think, generally speaking, exponential models here are more accurate. But let's just see. I'm just going to type in the formula as is. I'm trying to go quickly here. Negative 3,500 times the time, and no dollar signs there, plus 25,000. There's my linear model. Get rid of those. My exponential model. Be 25,000 times 0.86 to the t power, which is B13. It's going to give me different numbers. The linear one can't be correct forever because it eventually tells you have a negative value, and even junk scrap metal has value to it. So the linear model can't be accurate forever. Is the exponential model accurate? Again, I don't know for sure, but it seems reasonable, and I believe that's what people often use when they're doing accounting, doing depreciation for accounting. As far as answering the questions, after 3 years, the linear model predicts a value of 14,500, while the exponential model predicts a value close to 16,000. When will it be $6,000 in value? The linear model predicts an answer between t equals 5 and 6. I forgot what the old answer was that we got by hand. Got a piece of paper here with it on here somewhere. Thought I saw it. Oh, this is wasting time. Oh, about 5 point, here I found it. About 5.43 years. While the exponential model predicts somewhere between 9 and 10 years, maybe about 9.5 years. And then you can graph these things too. Make a quick graph to show you the differences between them. I highlighted everything, do a scatter plot. There we go, there's the difference between the graphs. They both go down at the same rate initially, approximately, but then the linear one becomes unrealistic and goes negative, whereas the exponential is maybe more realistic. You're assuming the value is going down by 14% each year when your discount factor is 86%. And that seems to be what we see here, and I don't know why that happened there. But I think I'll end the video here. Looks like it copied itself. There we go. I'll end the video there, and I encourage you to spend some time thinking about this.